everybody. I hope you made it safely from the lobby into the training room. My name is Henrik Ruscher. I'm working for Wiki. And today my topic is about adding a scalar transport equation to scalar transport form. The point of this exercise is to make you familiarize with how to code in OpenFOAM and how to use the what I would call a domain-specific language in OpenFOAM. And it will also be a code walkthrough. So just to give you an idea of what this session is about, it will be a code walkthrough through scalarTransportFoam. We'll pick up the code, we will modify it, we will run an example, add the transport scalar equation, change the FV schemes and FV solution file, change the inputs, just so that you know. Sometimes people are a little bit disappointed about the training, but I think it fits quite well into the overall framework of the trainings that we provide in the workshop. Usually I do this very interactively, in the sense of people shouting at me what they would like to learn and what they want to. I will also ask you questions, and we need to see how that goes. And so please use the chat and ask me questions or answer my questions. And there is time, yeah, we have 1.5 hours, and we don't have that much to cover, although it gets a bit frantic on the last few minutes to add actually the transport scalar equation. Yeah, just let me know if there is something that you always ask yourself about OpenFOAM, or I mean related to what we are covering in the training. Then just let me know, write a question, and I'll try and answer it. I have a second screen on my side, so I will try and respond. Okay, so scalarTransportFoam is a very small little tutorial case and application, and it solves a single transport equation. So it's the time derivative, diffusion term, convection term equals to a source, potentially a source. I will use a rather old version of FOAM Extend, which doesn't have FV options. So just in case you are initiated about that, so that allows you to have dynamically add some source terms. But the version that I'm using is plain and simple, and that's actually why I'm using it, to be plain and simple and more in the original spirit of OpenFOAM. Okay, so what we will do first is we'll pick up the tutorial case and run the standard program, scalarTransportFoam, on it, just so that you see what scalarTransportFoam is doing and how it works and what goes in and what goes out. And then we'll have a look at the source code to understand how it is built and how a typical OpenFOAM solver looks like. And it will help you to understand the more complicated solvers that we have in OpenFOAM. Okay, so I made myself a home. As you see, there is an OpenFOAM Workshop 16 directory. Can you see all my screen? Is anybody live? You're not attached to your keyboard, yeah? Anybody there? Ah, wonderful. Yeah, so you are alive. That's good to see. Normally I can see your faces, and that's much easier. But so if something is wrong, yeah, just let me know. I'm here, and I'll try to adjust things like I mean, I don't know, font, the size or whatever. Yeah, so if you can see properly, then that is all just beautiful. Cannot see the screen. Are you sharing? Aha. You see? What can I say? Good, you said that. So now better? Perfect. Yeah, we tried. And then, yeah, obviously we switched the screen for the intro page. And yeah, I forgot to reshare. So here we go. As you can see, I made myself a little directory, OpenFOAM Workshop 16. And what I will do is I will copy a case. And as you might know, we have the foam foam environment comes with some variables like foam tutorials. And that's set automatically if you install and source OpenFOAM correctly. And in basic, we have basic, very simple tutorials. One is scalarTransportFoam. I will not go around it, and I will pick up the PITS daily case. Usually there is a chance that you can do it live, but I think we'll not try here because it's too hard. So just follow what I'm doing and in the screen, and keep asking questions so we get some interactivity going. So I copied the PITS daily case. This is basically the same routine that you should be doing if you pick up your first tutorial. I guess that was the cavity. And you copy it into your home directory to be able to modify and run it and not pollute the distribution. So I'll enter it. And this should be familiar to you as a 0 directory, as a constant directory, and a system directory. So looks like an OpenFOAM case to me. And because I picked it from basic scalarTransportFoam, I also know which executable I have to run on it, which is scalarTransportFoam, which is not very surprising. And I can run it. Oh, and it dumps a bug, an error on me. So it's also, this is a good chance of going through error messages and trying to explain why the error messages are the way they are in OpenFOAM. Because sometimes it's a bit, yeah, it needs to get the, it doesn't, OpenFOAM doesn't quite say what it means all the time. So, but rather it, because it's a library and the executables are based on a library, sometimes the error messages are a bit difficult to understand. But here, what it says, it's I cannot find the file points, which is in directory polymesh. And because you have some experience with OpenFOAM, you know by now what is going wrong. And it's missing a mesh. And we can verify. So if we look into constant polymesh, yeah, we have a block mesh dict, which can be run with block mesh to generate a mesh, but there is no points, which is the file that is obviously missing. But there is other files that are used to make up a mesh. Okay, so that is missing. And what I need to run is block mesh, which takes the block mesh dict and makes a new a mesh from it. And if I verify, if I go back to constant polymesh, I have a bunch of new files, faces, neighbors, the points that were missing, and everything is there. And now I can run my scalarTransportFoam. So the reason why I'm jumping straight in here is I'm just running it to show you the solution, so you get a better understanding of what scalarTransportFoam is doing and what it is not doing. And that will help you to understand the code a little bit better. So that's why I'm sort of jumping into running the solution straight away. And my next step is Paraform, which allows me to visualize our solution. So I jump straight to the end of my solution, and I'm going to visualize a field called T, and that looks like this. So what we have here is there is a red area on the left. This is the inlet. So the flow is coming through here where I have my cursor to the top left. This is the geometry, the combustor, but it's misused in this example. So it's coming in here. There is a vortex, which I can visualize for you. There we go. So vectors, maybe some color, and let's make them a bit smaller. Here we go. So I'll switch off my temperature. So this is my velocity field. And what scalarTransportFoam is not doing, it is not calculating this flow field. But the only thing it's doing, it is calculating the following scalar. So that's a misconception or that I heard a lot of, or that I get from a lot of people asking me questions. But the flow field is, so to speak, an initial condition, or even more, it's a constant. The whole field is a constant, and it's kept constant over the whole duration of the run of scalarTransportFoam. And all that's happening is we are transporting our scalar that is called T, which is 1 at the inlet, through our domain step by step by step, going around in the circle, in the recirculation zone, out into a steady state. Okay. So that's all there is and nothing else. So do you have questions up to here? Okay, I have one. How is scalarTransportFoam and what we are doing now different from the scalar transport tracer gas function object? Nothing, except for it is a function object. So there is, in order to understand the function object and the tracer gas, it's basically scalarTransportFoam, but in a function object. So nothing, but I can now look at the code of scalarTransportFoam and understand in a very simplistic way of what OpenFOAM is designed for. If you understand the function object, then maybe this course is too basic for you. So I just warn you. But avoid disappointment. But yeah, it fits into the how to learn OpenFOAM framework. So it's a basic advanced training, so to speak. Does that answer your question? I hope it's still useful, but you tell me after the training. Okay, so so far so good. And yes, I mean this tracing or the transport, that can be done in several ways. But this is basically the very core application. And as you can imagine, this is one of the first applications that were ever written using OpenFOAM. And let's have a look at what goes in and what goes out. So there is the 0 directory. And in here, we have the field U. We can just open this up for you. And as I said, this is a constant. It's a constant field. This file, it is red, but it's never changed. And we have the T. This is our transported scalar. And it has the dimensions of temperature. So kilogram, meter, second, Kelvin. So this is our temperature. Could have any other dimension. If you want to think species, then it could be something else. The inlet, it has a value of 1, and the rest is 0 gradient up to the outlet, and also for the walls. Okay, so that's what we have. Oops, are we still here? Yeah, we are still here. Okay, so constant directory, there isn't very much in here either. We have the polymesh that we looked at, transport properties. There's only one property, and that's the diffusivity in the Laplacian that we need. So, and as you know, these are the time directories of our output. So depending on what we have in system control dict, we can adjust the amount of writing that is done. And you can figure there is a runtime, and it goes up to 0.1 seconds. You can also verify that system control dict. So start time 0, some delta t, end time 0.1, write interval every 50 iterations. So nothing too surprising, and nothing too exciting so far. But this one will take out. Okay, so what I promised was to have a look at scalarTransportFoam, which is basically driving this case and moving the T field in time. So any idea where I can find that? Any suggestions? So where would I find the source code for scalarTransportFoam? Okay, in that case, you are just in the right training, because I will help you. You know that you found your case, and that was in basic scalarTransportFoam. OpenFOAM, as I said, it sets up a bunch of environment variables that are called foam. So if I do, there is just quite a lot of them, but here we go. Foam. Here we go. So the one that we used before was foam tutorials. But there is also a bunch of variables that put where to look for the executables. And there's also one that is pointing to the source, which is foam source. And then there is another one that is a bit more specific that points to the solvers, foam solvers. Okay, so what I can do is I can do for CD foam solvers, which takes me to the solvers. The solvers, there is about 200, I think, of them. but they are grouped by what we call physics segments. And there is a one-to-one mapping between the solvers and the tutorials. So we used a tutorial. It was basic scalarTransportFoam. And not so surprisingly, we find also a basic directory here in the solvers directory. By the way, this took me to the installation of OpenFOAM, which in my case is in OpenFOAM, Foam Extended 4.1 application solvers. That path will obviously vary depending on what kind of version of OpenFOAM you've installed. But this lovely variable, it will always take you into the right place. Just in case you have several installed, then obviously confusion can happen easily. So I'll enter basic. And in basic, I have potential foam, Laplacian foam, and the one that we want to look at, scalarTransportFoam. So I'm in here, and what we find here is a scalarTransportFoam.c, which is the source file, the source code, the C++ source code for making scalarTransportFoam. And that one I will open. And in the next few minutes, what we will do is we will go through scalarTransportFoam line by line and explain, or I will explain, what each of the lines is doing and how the things are hanging together also with the case directory. And so that's the plan. I will not explain you what the comments, so the first bunch is also comments. Yeah, so that is not important. It's just telling you what the source code contains. And the next two lines are include directives. So in case you're not so familiar with C++ or with programming, what these include files do is they take this file, a file fvcfd, and the compiler inserts it exactly at this position in the file. So it avoids having to write out the same thing multiple times. And in fact, it is used in C and in C++, especially to declare a number of classes. So as you probably know, there is no class fvcfd in OpenFOAM. But what happens here is that fvcfd has more include statements. And we will exactly try and find out how that is happening and how we can find out which file is actually used. So what we see here is there's a depth file, and this file has moved into the make directory in later versions of OpenFOAM. So if you don't find it, just keep searching a bit into make, but it's still there. So it hasn't been disappeared. So if I open scalarTransportFoam.deb, this is a file that is generated by the make system of OpenFOAM. And here in the third line, I see my fvcfd file, and also I see the path. So if I take that and put it on my command line, there is a variable. Also, this variable is set in your environment. If I fire that up, I get fvcfd. And fvcfd includes, as I said, a number of files. Object registry, foam time, fvmesh, fvc. And those files is basically the important things that you need to do, that you need to include to do finite volume CFD with OpenFOAM. So now you learned two things. Well, includes, you probably knew already, but you also know how to find the file that has been included by OpenFOAM through the dep dependency file mechanism. And the good thing about using dep, with that one, you are absolutely sure that that file is actually included. If you start searching, like with find or with something else in the source tree, although we shouldn't have duplicate files, you're not 100%, you cannot be 100% sure that this file will be included. But with the dep, this is definitely the file that is picked up. Okay, so that's the dep. And so what is happening here is for the C++, a number of classes are defined. And they will be used later in the program. Simple control, that's actually a class that's also included that defines a class simple control that is used later. Actually, it's used right here. Okay, so much so for now. We have the next one is actually where the program starts. Int main is where everything starts. And that makes this include file here, this include statement, very different from the include here. Not the mechanics. It's still a directive for the C++ preprocessor. So a file will be included. But what is in the set root case, semantically, C++ is different from what is included up here. Because this is actually executable code. And here, on the top, we only have declarations. So I'll open it, the set root case. First of all, I will find out where it is using the dep. Okay, so if we go down, set root case, so it's almost at the end. So I'll open it. Okay, so what we see here is it's quite different from a declaration in the sense that these are statements that actually do something. And in this case here, we have arc list arcs that is making a variable arcs, and this one is an if statement. And normally, this is when the computer scientists, they keep jumping on me at this point because they say, no, this shouldn't be in a header. And they are right. So we are including a header file, .h, which should contain only declarations. But in fact, we are also here, we are including statements. We are not going to change the code, but for you, it's probably good to know that these are not header files. They cannot be header. You cannot declare new classes in any function, but you can declare and use instances or declare variables out of classes, but you cannot make new types. so to speak. Why is that? So why are we using it? It's because setRootCase contains functionality that is almost used by any application or utility or solver in OpenFOAM. So in order not to duplicate the code, it is put into a .h file and included into all of the top level solvers. So setRootCase, now we can think about what it is doing. What setRootCase does is actually quite simple. So the first thing, it declares this variable args, and it's of type argList, and it declares it, or it instantiates this variable from two other variables, argc and argv, and those are coming from here. And these are the command line options that you might give to the executable, just in case. That's the same in C or C++. And so what is happening here is the argList is being parsed, and then it can be queried. And here there's an exception being thrown in case we are not in a case, or root and case are not specified in the correctly. So that's all that this file is doing. And the next one is create time. So create time. That one is included here. So create time, it throws an info statement saying create time. And secondly, it creates an object called Runtime, which is of type time. And it uses the arguments on the command line and also a constant. Okay, so runtime is actually quite an important class in OpenFOAM, and it has a multitude of functionalities that are combined. Yeah, so one is it keeps track of time, and there isn't one. There's not just one time in OpenFOAM. There is the time that you use for the simulation. You can say iteration counter or computational time, which steps up with every iteration. So that is one type of time. Then it keeps time of wall clock time. So the time that elapsed while running the code, which is also reported after every iteration and at the end of the run. So that's also kept in time. And another functionality of time is it is the object registry, or the main object registry. And the object registry in OpenFOAM, it's a place where we keep track of the large objects that are instantiated during the execution of OpenFOAM. And the important ones are obviously the mesh, but also all the fields that are registered on a mesh. Like in our case, our volume vector field U and the time, the temperature T. And the reason why we need the object registry is because you need to be able to have access to data that you don't have a reference of. Let's say, just imagine you are in a boundary condition for the velocity, but you need the density and the temperature to evaluate the boundary condition. So you could have very big fat interfaces and passing all the variables around. But obviously that will become very static and clumsy. So what happens here is that in OpenFOAM, and also because of the dynamic nature of OpenFOAM, it's being a library used for different applications. So the type of fields is not really known. We don't even know whether we have a velocity or not. That's why everything is registered. And as long as you have access to the object registry, you can always find out about other fields that exist in OpenFOAM or in the run that you are executing. And one example is our boundary conditions, and that's probably the most obvious one. But there is a lots of funny, fancy uses for the object registry. So where is it made? Right here in create time. So that's the mother of all object registries. It's also hierarchical with different layers, but this is the one that is most important. Okay, so how are you? Are you still online? Nobody there? Wait. Maybe I need to clean it up here a bit. Sorry, I need to clean it up. No, there's a lot of them. Here we go. I need to clean up the chat a bit, because otherwise I don't see your new messages. Okay. Yes. Okay, so I have one question about the object registry. And it says, could you please explain object registry again and how it is used in OpenFOAM and what it is used for? I couldn't understand it fully. Okay. So, if you imagine yourself writing code, software, for a boundary condition, then it is not, for example, then it's not so clear. Then you need other fields to evaluate the boundary condition other than the one that you are writing the boundary condition for. So, for example, you want to write a mass flow boundary condition. You set the mass flow, like X kilos per second. You want to set the velocity. That's all fine, but you need the density to evaluate the velocity. Okay, so because you're sitting in that boundary condition and we are not writing interpreted code, it's all compiled together, there isn't, you have no access to that data. You don't have access to the density field in that example. So how do you get hold of it? And also in a dynamic manner. And that's what the object registry is for, because within the velocity boundary condition, I can ask for other fields. For example, the density. And I can then use that density to evaluate my boundary conditions. And there is a million other uses. Does that help you? Aha, okay, wonderful. So I'll take that one off. Okay, so I have one more question here. That is, the start and the end time do not have an impact on the final solution. Well, in this case, well, the end time, it could be made longer, yeah, for example, but and then it wouldn't change because the scalar transport form, it goes into a steady state. But if I change start time in the current tutorial, then it will not find the start. Yeah? So I can demonstrate, yeah. I think that's the easiest. So if I go here, so if you remember, when I picked up the case, it was like that, yeah. So that I only created the mesh, but the time directories were not here. So if it was independent of the start time, and let's say if I understand correctly, and I set here, I set the start time to 0.1, that will create an error. Because scalarTransportFoam, it will come up, it will say reading field T, and it will look in 0.1, and 0.1 directory doesn't exist. So I don't know. Maybe I didn't understand the question correctly, but I would say it depends on the start time, because it will throw an error if it cannot find the directory. If I rename the directory, then obviously it will start again. So yeah, I try to answer the question, but we can, if you write some more, then I can try to answer it a bit more. So then I have one. Apologies, but what did you do with the first error message? I ran block mesh to generate the points in polymesh, and then the error message goes away. This one we've done. Okay, so I think I cleaned it up. Okay. Okay, so I cleaned it up a bit in the chat. So I hope I didn't, if I, took somebody, deleted somebody's question and he feels it's not answered yet. Yeah, just type it again and I will try and answer. Okay, so you may notice that we have a little bit of rainfall and the thunderstorm here in Wernigerode. So it's raining. Let me close the window. Okay, so this is probably much better now. Okay. So more on scalarTransportFoam. So scalarTransportFoam. We've been through create time, create mesh. This one makes the simple variable. We're not going through that. Create fields. I think that is an important file. I just jumped over create mesh because we are potentially running out of time. What create mesh is, it creates a variable mesh. And what it really does it's reading constant polymesh, the files that we found there, boundary, cells, owners, neighbors, points, reads it in, and it creates an internal representation of the mesh. So, and it uses the runtime, by the way. So it registers the mesh with the runtime object registry. So what we find here in create fields is we make a bunch of volume fields. volume fields in foam, they are fields where the working variable lives in the center of the cell, in a finite volume spirit, so to speak. And they come in different flavors depending on the variable that lives in the cell. And one is a scalar, which is a single number, and our scalar t qualifies as that. So what you see here is a initialization of a variable. So if you are not so familiar with C++, you can think of this as, or maybe you are more into C, then this is something like a more complex version of int x equals 0 or something like that. I'm saying it's a more complex version because it takes more arguments. So this is one of the arguments that is passed. So if you want lazily, you want on the right-hand side of the equal. So that's one argument, and then there is a second one here. But that's why it is in brackets. And this type of construct in C++ is called a constructor. So all it does, it creates a variable with name t of a type volume scalar field using some arguments. And the first argument is an IO object, and the second one is our mesh. IO object, you can think of simplistically, you can think of it like it's a file handle. So what IO object does, it reads the file called t. And where does it read it? It reads it from a certain time. In this case, it asks runtime time name, which is in the beginning, it's set to start time. So that's why we actually, this is sort of making the connection to our error here. Yeah. So if start time is 0, then it looks at Pitts daily 0t. But because we set the start time to 0.1, it will look in 0.1t. And the reason why it knows is it's runtime. Apart from the functions that I explained, being object registry, wall time, and so on, it also is the representation of the system control dict. Because some of the entries that are in there, like start time, end time, time step, is used to advance time. So this is also the class that makes accessible the things that the input in system control dict. And it is used to read the right, to look in the right time directory or in the wrong one if you set it up incorrectly. There's a bunch of more things, but there's one thing that I usually ask, and that is, okay, so here I have t, and I have it twice. Okay, so can somebody explain me the difference between the two t's and why is there a need to actually have it twice? Okay, so nobody's answering, or at least I can't see it. Okay, so there is a difference. Yeah, if you think about C++, this one is in literal, so it's a string. So it's It's a string of one letter, and that is t. And this one is the variable name that we want to make. We want to make a volume scalar field, and we have to give it a name, and that is t. So this is the name of the variable that is used further down to actually use our variable t. And this one is the string. And we cannot use this variable name because once the compiler has gone through the code, it usually it loses all the names unless you do some fancy things with the code. But in C++, you cannot work out what the name of the variable was before you compiled it. And yeah, now to be sane, you want to keep this one the same. Now, I mean, obviously it is possible to use, let's say, a field Q and name it T. But maybe that is not a good idea because it will confuse you. Okay, so then there is another one, and this is just a bit different. That is our volume vector field. So instead of having a scalar, just a single variable, we have a vector, and we can read that just in the same way. That's our velocity field. And then we have one more. That is a bit different now. We are reading transport properties. You remember that is the file where the viscosity, the diffusivity for our scalar was given. And there is a new type. We are reading that in, and that's called the IO dictionary. Again, that is made from a file handle, IO object, transport properties. There is a different path that we get from runtime constant. Anyway, so what IO dictionary is, you can think of it as a representation in code, in software, at runtime of the file transport properties. And this is a complex hash table and lookup table. So we can start querying transport properties here, the IO dictionary transport property. And the simplest way we can do that is using lookup. So transport properties lookup and giving a name dt will look up the keyword dt in our transport property. So just to give you, here is our transport properties file. And the way it works is that we have a keyword and all the rest is the value that we are looking up. So what happens right here in the lookup, it says look up keyword dt, this one, and it returns this part. And then the later part, the value is parsed or used to create a dimension scalar which has the variable name dt. So, and this is all, these two constructs they get you a very long way with OpenFOAM and the IO in OpenFOAM. So what is a dimension scalar? A dimension scalar is a number or a scalar, a single number, but it has dimensions. And we will need those dimensions in order to do dimension checking in the equations that we are about to type. I will not talk about create phi, but what it does is, not in detail, but what it does, it creates a variable phi, which are the fluxes, out of the velocities in our case. So much, and we are done with create fields. And maybe it's a good time to review what we've done already. So we've passed our options that we pass to our executable. So everything that comes behind scalarTransportFoam as command line options. We are setting up, we're checking those arguments. We are creating one variable called time. We are creating another variable called mesh. We have simple. And in create field, we did, I don't know, we did T, U, transport properties, and the DT dimension scalar. I think that's about everything. Okay, fine. So not very much, yeah, just a bunch of rather complex variables that have been created up to this point. And the next step, I'll jump over current number, but there's a while loop, and this is what we call the time loop. So in here, the runtime is taken care of. So this is the main time loop. So every time step, so if you finish a time step here, at this point, the time will be incremented, and also the function objects will be called in dot loop. So this one we will skip, and the working part, and almost the only working part in this code, is the following: is the solve statement. So what does that? It solves this equation, and we talked about it. I already said that scalarTransportFoam, it solves a transport equation for a single scalar with a time derivative, a convection term, and the diffusion term. And that's what it does. So the velocity goes into the convection term through the fluxes phi, which I said is just a different representation of the velocities, at least for the use that we have here. The Laplacian has a constant dt, and we know that guy from the create field. So this is our diffusion coefficient. And the time derivative, it doesn't have another constant, so it just goes dt over time. So what happens here in the code is that this is why we have Fvm here. So Fvm, all the operators with Fvm, they produce matrices. Matrices, I mean, it's a bit of a misleading terminology in OpenFOAM, but what really is created is a linear equation system. So a matrix A times a solution variable T, which is here, times a source, not equal a source. And we get different parts of the of this linear equation system, and we bolt them together with the operators that are here. So this is a fancy use of operator overloading in C++, and it creates a domain-specific language to solve finite volume numerics. So I have a bunch of questions here. I'll see. I'll check at least one. Okay, so one is going about create fields. I'll jump back. We'll go there later, and I'll pick up that questions. So it's about out of right and false. Okay, that one will come back. First name of the field. Yeah, that's correct. Thank you. Okay. So can you elaborate about adding the turbulent diffusion coefficient in the case of turbulent flow? Okay. So in turbulent flow, the turbulent this coefficient, it would be a field. in fact. So the diffusivity will depend on the local state of the flow. So if you think of K epsilon, then it will be mu K over epsilon something. So it will be a function of the state variables of your turbulence model. And the way that this is done in OpenFOAM, so the mechanics is relatively simple. The turbulence model, you can ask for the turbulent diffusion field. And in the Laplacian, all that happens is that other than here, it's a constant. Yeah. So diffusivity is 0.01 all over. And with turbulent diffusion or with a turbulence model, this becomes a locally varying field. And that's how it hangs together. Of course, there is more complicated situations. Yeah, when you talk about multi-species diffusion, Maxwell, and so on. But at the first step, like fiction diffusion, then it will be hanging together like this. Okay, I hope that answers your question. I'll need to move on because we want to add a transport equation and we only have half an hour left. And we also have a question on the way about the auto write. Okay, we'll have to do that in steps. I'm not going to do a full another equation straight away. So what I would like to do as a first step is I would like to add a source term. And the way I do that is I need a source term. And I will add it here as a dimension scalar. So I give it a name. So what I'm not adding the code at the moment, I'm adding the input that I want to use. And I do that quite frequently. Yeah. So what I do is I massage my input deck to give me the inputs that I would like to use. And then I start writing the code afterwards, just to structure the inputs. And then I write the code to use it. So in our case, I would like to have a constant source term. And well, I don't know, it should be 10. Okay, so I added it in the transport properties file and I would like to read it. So where would I read it? Can you tell me what I need to modify in my OpenFOAM source code to read this property? Create fields. Oh, wonderful. Thank you. Yes. So I go down here and it is, it's a dimensioned scalar. Here we go. So I called it source T. 1, 2. I'll make it the same. Ah, okay. I missed one important step, and that was I'm still living here in the distribution. That of course is not a good thing. I'm allowed to save, but your system administrator probably does not allow you to do that. So one thing we need to do before we can modify the source of scalarTransportFoam that we have been staring at is we need to copy it to your home directory. Okay. So, and now I need to close these windows. To avoid confusion. I will do that a little bit quicker here so that we can actually add the transport equation. So when you move a code like scalarTransportFoam into your own directory, it's important that you rename it. So what I do here is in make files, I change the name of my source code. And the reason why you do that is you don't want to have two executables with the same name. It will create confusion sooner or later. So it's good practice that you keep renaming it. And you have to do it in several places. One is the source code. That was the .c file, but also the executable name. And the thing that I forgot is, because I picked it up from the distribution, it is writing it into the into foam app bin. But ideally it should write it into user space. Now, why is that? Okay. Okay. So now I have a new software called my scalarTransportFoam. But so far it's the same source code, it's compiled, so it will do the same thing as before. So the first thing I usually do, I put an info statement in. I recompile it. And then I can run it. If I remove the bugs that I put in. Okay, and it runs. And it also talks about a misspelled Wernigerode in Germany. So perfect. So that serves two purposes. I know that I can compile the code and it doesn't have bugs after copying and linking and all the rest of it. And I also know that I'm compiling the correct file. So call me paranoid, but I've seen it going wrong so many times. So I thought I share that obvious wisdom. Okay, so now we are in a good position. Now we can start changing create fields. I'll move that a little bit down. Here we go. Create fields. So what we were about to do, actually I copied it. I saved it before copying. So we already have a dimension scalar, source t, and we can do something like that. We can do an info on that, just to get a bit used to the feeling of modifying the code and compiling it. So to compile, you use wmake. That fires up the make system in OpenFOAM, creates the dep file, and so on. So here we go. Here's our new info statement, and it goes source t. Those are the dimensions and the value, and it's a copy of what we put in. I don't think I'll have to demonstrate that if I change the transport properties that this output will change. I think you will believe me. And the question to you is, what do I have to do to add that source to my transport equation? Okay. Okay, so it's a source term. And the way you add a source term to the transport equation in OpenFOAM, there is an operator, it's called equal equal. And basically that means we are adding the source on the right-hand side. So equal equal source t is one way. I could also write minus source t. And what that does, it subtracts the value 10 or whatever is in source t from the right-hand side in the linear equation system that is generated in these 3 lines. And then that is passed to the solver, and our field t is updated. So both is equivalent. Equal equal maybe a bit easier, whatever. But it does exactly the same thing. So now we subtracted source t, the dimensioned scalar source t, from the Fv matrix that is generated from those 3 statements. Okay, that has compiled, and we can run our code. And surprise, surprise, it didn't work. And what it says is that there's incompatible dimensions for an operation. It can only be one operation, namely the one that we edit, and that is the source term. And what it tries to tell us here is that the dimensions for the source are not corresponding to the dimensions that are required by the equation. And I told you that OpenFOAM is doing dimension checking. And that's why we have to give the dimensions in the fields for the dimension scalars and so on in order to facilitate the dimension checking. And yeah, it's quickly done. I didn't think about it here. But the dimensions that we get from here is Kelvin, yeah, for the temperature over time. So we should have Kelvin over time. But because I copied straightforwardly the dimensions from our diffusion coefficient, which is kilogram meter squared per second, there is a mismatch in the in our dimensions. So what I have to do is I have to give it kelvins per second. And then it's going to run. So, no, that does not belong here. So if I load t and then look at t, well, you see it's not red in this corner, but it's becoming red, and also it's not bounded between 0 and 1. So maximum is now 1.5. So yes, the simulation has changed. And what is happening now is that there is a gradual source term going from here, adding a little bit of t in every cell. And it's going around. Okay, so that's a uniform source term. And the next thing I would like to do is to add another transport equation. And the way I can do that is I can simply copy our source statement. Yeah, but what I want is I want to use a different variable. Well, how about t2? Let's make it, yeah, t2. It's a nice one. So I can compile that. I can try to compile that. Yes, I got a question here. Can we add a source term at a specific location? Yes. The way you do that is that you cannot do that with the dimension scalar, because the dimension scalar is just a single number. But if you make the source t a field, a scalar field, a volume scalar field, then obviously that can vary in space. And now the question is how will it vary in space, and how will you make it vary in space? And there is different tools of how you could set it. Yeah, I mean there's a multitude of it. So basically what boils down to is you make yourself a volume scalar field, and the question is how are you going to set it? What kind of utility are you going to use to make your source vary in space? And once you do that, you write the file, you read it in, and then you have a source that varies in space. That is just one way, but there's more than that. But this one fits into the story that I'm telling. Okay, does that help? Petros? Mm-hmm. Thank you. Okay. So there's a question from Benjamin. How could you comment on how the passive scalar variable can be physically interpreted? For example, using ppm per million concentration of a tracer fluid bounded to 1. Yeah, well, I guess the easiest interpretation here is actually to say it's temperature, yeah. But then it's yeah. I mean, you can say temperature is a passive scalar. Well, I would say a passive scalar can have any dimensions. Yeah, it's what it only thing that it says is because why it is passive. It is just that it doesn't interact with any other equation in the system. But what you put on is when you think of it as ppms, and it would be dimensionless. Yeah, you can choose, but I think it needs to map with the dimensions. And here my T is has temperature, so I would To be consistent, my interpretation would be that this is temperature as a passive scalar. I hope that helps and wasn't quite too confusing. Why FE? Okay, so why FEC instead of FVM? I'll feed that in. Okay, so FVM makes a matrix, so or a linear equation system, and FEC stands for finite volume calculus. And what FEC does, it takes a field or several fields and makes a new field. So think of the gradient or the magnitude or something like that. So you take something, you calculate something, and that is your output. And that is what the calculus does, opposed to the finite volume matrix. Because the finite volume matrix, it builds a linear equation system, which then needs to be put to the solve statement. And when you see something like this, FEC grad something. Yeah. Okay. So now you could say, okay, what is this FEC doing with all these linear equations? Well, it's quite easy because what this FEC needs to do is it needs to make a source, and then that source becomes a source term for the equation that we are going to solve. Here, it doesn't make much sense because the gradient will always create a vector, and that will not fit with the, well, we haven't said what T2 is, yeah. So, but anyway, so it needs to map vector, scalar, and so on. I need to push on a bit because now I need to make myself a T2 so that we can get a nice little transport equation. And what I do is I will just rip it out here. I will copy it. I will make a duplication. Okay. And now, at least my code is gonna compile. So this also was the point where I wanted to say auto write and no write. And that's the question that is still pending. These flags, they will set the way that the field is interacting with the I/O. So the first one is how you will read. Here it's must read, which means if the file doesn't exist on disk, you will flag an error. There is also ways of generating, creating the fields from expressions in case the file is not there, which is read if present, things like that. And auto write is what shall I do when I come to the write statement in the code, which is here. If I come here and it says auto write and it's time to write, in that case, the file is written. So when am I going to do that? Well, all of the files that I would like to look at later that need to be auto write, but more essentially, all of the files that I want to restart from need to be auto write. So now I have to really, really, really push on. And I hope this answers the question about auto write, at least in a fast way. So if I start my code, I can see one change, and that is reading field T2. So it is reading, and it is reading it from 0. And my problem is well, I added it to my source code and I compiled it, but nobody has made a new field and of name T2. And I will change it a bit so that it has some difference. And so that's my field T2. And that fixes my first question. I will first bug, first error message. And I keep going through the other error messages just to show you what effect, what I have to add to the case in order to make it work with the new code. And one error that is coming is Laplacian DDT. And that problem is in FE schemes because I have a new equation for a new variable, T2. And that means unless I have defaults, I need to add schemes, discretization schemes for all of the new terms in my new equation. There's two terms. I need to add two places, and then one more thing, and that is in FE solution. Now I have a linear equation system created for a variable T2, which I would like to solve, but I haven't said what kind of solver I wish to use. I want to use the same as for T. And now I got it to run. And as you can see from the output, I now have I'm now solving two transport equations. And if we go back into our case, and the second field appears. And if we T2, I'm a bit confused because I expected that to be on the inlet to be 2, but at least the field exists. I'm just a bit confused on why it isn't 2 at the inlet. But I think we need to leave it at that if we want to have one or two more questions. So change to 2.2. Ah, thank you. Too easy. Thank you. Thank you. Yeah. Okay. I have one question. In case we have transport in porous media and consider non-isothermal conditions, is it the same way you will add the temperature equation? Yeah, in principle, yes. I mean, this is exactly any transport equation you will in OpenFOAM that is discretized with finite volume will be added in this way. They will just look more and more complex. So for porous media, you will have to do something with the fluxes, yeah, to take into account the blockage. So either it's in the fluxes, or there is something in the time derivative because some of the volume is taken up by some solid. It also depends on how you do the specification, yeah, how you define fluxes, how do you define volume and porosity. But yes, essentially, this is what you do, and just the coefficients become a bit more complicated, and they can all vary in space, as I've shown. So I think time is up. If you want some more last question or ask me something later on in the chat, please feel free to do so. I hope you enjoyed and had a good time and picked something up. So thank you very much for listening, and bye-bye.